this is part 1 of lesson 5.2, exploring translations of quadratic relations, specifically using this form over here. This form is called the vertex form, which allows you essentially to find the vertex of the parabola very easily. So we're going to investigate the roles of h and k in these forms. So we're going to take a look at the roles of k and y is equal to x squared plus k, and y is equal to a brackets x minus h squared, and also this full form over here, y is equal to a x minus h squared plus k. So very quickly I'm going to illustrate that what this form lets you to determine. So you'll notice you have the values h and k here. When you have a quadratic relation written in this vertex form, you can figure out the vertex at a glimpse by basically just taking the h value in here and changing its sign. So this negative h becomes h. That would be the x coordinate of your vertex. And then k would be the y coordinate of your vertex. So if it was x minus 3 squared plus 5, you would have plus 3 and 5 as your vertex. And we'll see more examples of that in just a bit. So we're going to start off with the role of k in examples like this over here. So what you have here are some quadratic relations, and they are technically in the vertex form, but their vertex form would have something a little along the lines of this. They would have y is equal to a x squared minus h, but in this case their h is 0, plus k. And so in reality that would be something along these lines here, or I shouldn't say x squared here, let me erase that. X minus 0 squared plus k. So in reality it would look something like this. You would have a, and then x minus 0 is just x squared, so ax squared plus k. So when h is 0, you basically just have your x squared, your ax squared, plus or minus your k value. So in each of these situations here, our h is 0. Remember that the vertex is always going to be your h, k coordinate. So we know that all of these relations here have the x for the vertex is 0. So now we just have to find k. And k is just that other value that follows, the plus or the minus that follows after. So in this case, there's no plus or minus that follows this x squared. So what that means is it's plus 0, which means the vertex is at 0, 0. In this case here, we have plus 2. So the vertex is at 0 because of the h, and 2 because of that k. So our k is 2 here, our k is 0 here. Over here, you can try it yourself, pause the video, and see if you're on the right track. So first find your k in this expression here. If you found your k was negative 2, you're right. As a result, your vertex is going to be 0, negative 2. So when you have this form here, it is technically a vertex form where the h is 0, and as a result, you don't have this bracket here squared. You just have ax squared, and then you can have your k after. If you only see x squared, that means that your k is 0 and your h is 0 as well. Here we have our k's being positive 2 and negative 2, as opposed to our h's, which are 0. So what we're going to do is we're going to take a look at, well, so what? What does that do? What do the h and k, what did they do to my x squared graph? Remember, our goal is always to put x squared first, and then compare how these changes that we applied to the x squared affected the graph overall, and we'll come up with a general conclusion. So you should know how to fill in a table of values. We're going to do that for each of these relations here. We'll do that fairly quickly, just to, because you have had experience with it so far. So if we go through the table of values, at negative 3, we have 9 for the x squared relation. We have 11 for the x squared plus 2. And then over here, we have 9 minus 2, so 7 for that one. Then I'll just go down, continue here for 1, 0, 0, 1, and 4. And then for our 3 back to 9. Then over here we have 6, 3, 2, 3, 6, and then back to 11. We don't really need all these points. I'm probably just going to graph the -2, -1, 0, 1, and 2. But you can definitely have another point there if you need it. And then over here we have 2, -1, -2, -1, let's just see, 2, -1, -2, -1, and 2 here, and then back to 7 over here. So now we have all our table of values for our different relations provided to us, and we're going to go and plot these on the same grid to see what the effect of changing that k was. So how did +2 change my x squared? How did -2 change the x squared? We'll start off by drawing the x squared. We can go up by units of 1, so that should work just fine. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have our negatives this way, -1, -2, keep going that way, -4, -5, -6, -7. This is our x-axis, this is our y-axis over here. And then same thing here, 1, 2, 3 on our positive side, 4, 5, 6, 7. Make sure you do label your graph. It is very easy to make a mistake. In the spur of the moment when you're doing a test or a quiz, there's stress happening, and it's so easy to just count incorrectly and go in the wrong direction. So let's go and plot our points. So when we're at -3, we have 9 for the x squared parabola. When we are at -2, we have 4 for the x squared parabola. At -1, we have 1. Our vertex is at 0, 0, because we have our h of 0, k of 0. And then we can go and find the symmetrical sides on the other side, or just plot the points as you see them there. So at -2, at 2 or 4, and at 3 we're 9. And then we can connect those dots and label the graph. Again, you would do a better job than I am, because you would have a pencil with you and you'd be taking your time. And so this is y is equal to x squared. We'll use a different color for the other graph, the x squared plus 2. So when we're at -3, it's 11. That's off our chart, so we won't worry about that. When we're at -2, we have 6. Oops. When we're at -1, we have 1. So that works. Oh, sorry, we have 3. So this is 1, 2, and 3. When we are at 0, we have 2. When we're at 1, we have 3. When we're at 2, we have 6. And then we can connect those dots together. And of course, you could always extend your graph if you knew other points. Let's extend this one as well. Let's label this one as y is equal to x squared plus 2. And then we'll go and plot our last graph here. Let's use a different color. Let's do this blue over here. So when we have -2, we are 2 over here. So -2, we are 2. For -1, we're at -1. For 0, we're at -2. For 1, we are at -1. For 2, we are at 2. And then for 3 and -3, we're at 7. So we can plot those in there. 3 up there, and -3 up there, and we can just connect those dots, extend, and we label y is equal to x squared minus 2. And let's make sure that one's actually 7. So 3 squared is 9 minus 2 is 7. That's right. So if you take a look at the graph carefully, we'll analyze it. Here we have x squared in red, and then here we have x squared plus 2. And let's look at the equivalent points. For x squared, when you're at 1, y is 1. But for x squared plus 2, when you're at 1, y is 3. Notice the y value are 2 units apart here. It's like the x squared value was moved 2 units up for that. Let's look at another point. When you're at 2 for x squared, you have 4. But when you have x squared plus 2, you have 6. So again, 4 to 6 is 2 units up. Take a look at this graph here compared to x squared. So the x squared minus 2 over here. When you're at 0 for x squared, you have 0 as your y. When you're at 0 for x squared minus 2, you have minus 2 as your y. Let's look over here. When you're at negative 1 for x squared graph, you're at 1 for your y. Where you're at negative 1 for your x squared minus 2 graph, you're at negative 1, which is 2 down. So maybe you're getting the hang of this, or the pattern here, but it looks like the k moves your parabola up or down by the number of units that it has. So for example, it looks like my plus 2 moved my x squared parabola up 2 units for every y value. And it looked like my minus 2 moved the parabola down 2 units for every y value. So maybe we're onto something there. I think we are. So how are the graphs of b and c related to the graph of x squared? Well, let's take a look. This over here, that plus 2, means that the x squared graph, so this is the x squared graph, essentially translated, we call that a translation when you move the graph up or down. Translation upwards by 2 units. And it looks like this one over here, when you have a minus, it's a translation downwards, a downward translation. By 2 units. So here's what we know. This is our conclusion we can come up with. In the graph of y is equal to x squared plus k, this graph specifically is a vertical translation of x squared, meaning it's moved either up or down. So the x squared moves either up or down depending on what k is. If k is positive, the graph is translated upward by k units. K can be 5, it goes up 5. K can be 6, it goes up 6. If k is negative, the graph is translated downward by k units. And in this form here, the coordinates of the vertex are always going to be 0, k. So the vertex in this example here, for example, is 0, negative 2. In this example here, it's 0, 2, just like that. And our axis of symmetry for a graph of this form here, either x squared plus 0 or x squared plus k, where k is some number other than 0, is always going to be x is equal to 0. Because our parabola is always going to lie on that x is equal to 0 line right on the y-axis. So here's x equal to 0. This is our axis of symmetry for these types of parabolas with these types of equations. So if you can recognize that, you can easily find your vertex, you can easily find your axis of symmetry, and figure out how graphs are related. So let's look at question 3 over here. How are these graphs related to x squared? Well, we know this is an upwards translation, so upward translation by 5 units. Translation by 5 units. And we know the next one is a downward translation by 7. We'll finish this example in the next video.